Hi all, this is a brief lecture on the Lab 7 in our series of trying to get a process set up and properly tuned. So in Lab 7, we're going to be introducing some new terms and providing also for automatic cooling. So in the previous labs, we have already talked about the process variable and what it is. We've entered a set point and determined that the set point is the location where you want your process to control. And we've also looked at the control variable. And the control variable is the variable that we're going to use to actually control the system. In Lab 6, you also would have been, if we were on campus, looking at overshoot and undershoot in your particular system. Again, as to just collect some data for when we start tuning, because control systems need to be tuned so that they don't overshoot and so that they don't undershoot. There are several new terms that I want to introduce in this little lecture. And three of them are proportional gain, derivative gain, and integral gain. Take notice the designations for these is K sub P, K sub D, and K sub I. In Lab 7, we are just going to introduce proportional gain. Now, there are two basic structures behind control systems. And those of you who took my online class of Introduction to Process Control, we beat these two systems up pretty badly. And they are open loop and closed loop. And open loop systems are nothing more than a system that has no feedback on it. Feedback being we're not making a measurement of what really happened. So an input is provided to a controller. Say we want to turn on a fan. So we turn on the fan. The controller does the action of controlling the fan. The process is the fan's running. And out here we have fan running. Well, you have to ask yourself the question, if you can't see the fan, did it really start? We don't really know if it really started or not without any kind of feedback. We could have a motor controller, same situation. The motor controller will send a signal out to the motor to start. And maybe this motor is controlling a conveyor belt. And you can't see the conveyor belt because it's someplace else in the plant. Well, without any indication coming back to the control, did it really start? So is that conveyor actually running? But also, even if it was running, did something jam on the conveyor that maybe is jamming the conveyor from running? Again, we don't know. So we need to go to a closed loop system. And a closed loop system provides a measurement path whereby we have a command signal come in that has a set point. And I could have actually added another line in here for set point. And we send that signal, I'll come back to this error, to the controller to run the process. And then we make a measurement. And we take that measurement and compare it to the set point. Is it where I really want it to be? And if not, I'm going to make a correction. And we're going to use the error in the control system as our control mechanism. So we're going to look at how much error is in the control, and we're going to use that error to actually control the process. We'd like to have an error of 0. So let's look at this motor again. What we've done was we've added something called a rotary encoder onto the conveyor. Now it has to be added to a fixed axle. It cannot be put on like an idler belt or an idler pulley. It has to be on a fixed axle that's connected directly to the motor, either through gearing or directly. And all this does is it sends pulses back to the motor controller to let it know, you know what, I'm moving, I'm turning. So these pulses will be coming back to the motor controller. Now, not only can a rotary encoder let the controller know that the motor's running, it could also be used to tell it how far it has moved. So maybe we have 2048 pulses per revolution. So per revolution, maybe I get this number of pulses. And maybe per revolution, the conveyor moves 1 foot. So if at the controller, I measure or count 4,096 pulses, I know that the conveyor moved 2 foot. I can also tell the direction of movement, because a lot of these encoders have 2 channels on them, where one channel is out of phase with the other. So depending on which channel is out of phase, which one's leading and which one's lagging, I can also tell you what direction it's running. So feedback is a very important concept to getting a control to actually control. Now, to calculate the error, in our particular application, there's 2 equations that can be used. Error can be the process variable minus the set point. And notice I'm saying this is for cooling applications. Or error could be set point minus the process variable. And this is for heating applications. And if we look at the process that we were using in our lab, you might think that, well, this is a heating application, because all we've done is turn the heater on and off and provide it manual cooling. However, our application is actually a cooling application. Ours is actually a cooling application, and we will be using error is equal to the process variable minus the set point. It's a cooling application because we're using the fan to cool the cool the process. The fan is the control variable. It's what we're monitoring the temperature and adjusting the cooling to provide the correct temperature. So let's look at this graph again, and this time I don't have to draw it like last time. We know that this is overshoot, that this right in here is overshoot. We know this is undershoot. And we also know that this is error, because I'm not at my set point. Now this green curve is the ideal function. It's what we would like our process to be. But because I have error in the system, I need to do some tuning. So by looking at this, you can see that when my error is positive, the process is too hot. It needs cooling. So that means I have to turn the fan on. I have to make sure I turn it on. Do I turn it on full, or do I just turn it on slightly? In other words, how much cooling do I need? When my error is negative, the process is too cool. So I need heating, and I got to make sure my heater turns on and I have no cooling. So we're going to use this error signal to perform what we want to perform. So remember, I said we were going to say that error is going to equal the process variable minus the set point. Let's just make an assumption here. Let's say our set point is 100. And let's say our process variable peaked out here at 105. And this is degrees. So by applying this equation, we can say that our error is our process variable sitting at 105 degrees. Our set point was 100 degrees. Therefore, my error is 5. So we're going to do this. If I take my control variable, and I'm going to say my control variable, and in our case, it's going to be I want to get the fan to run. So I already know, you already know, because you made these measurements, where does your fan just start to turn on? And we called that something like the min fan value, or the min fan counts. So we know that this count value, and I'm just going to put a number in here. I'm not sure what that number might be. So let's say it's 2,948 counts. I could be way off from what you actually read before. So I know this is where my fan is just about ready to turn on. I'm going to then add the error to it. I want to make the fan turn on. I have to increase these counts. So let's add the error to it. And we're going to add 5. Well, my CV is now 2,953 counts. Is that change enough to get the fan running? And maybe running enough to get the cooling to occur? I doubt if 5 counts are going to make a big difference in how the fan runs. So we have to add another term called proportional gain. And that's the K sub P term, which is gain. Sometimes they just call this gain. And this gain is a tuning parameter. This is one of the items that a technician would adjust in an attempt to make the controller control the process. And we're going to modify this equation to now say that CV is going to equal our min fan counts plus the error times the controller gain. So the gain is nothing more than an amplifier. Think about it. An amplifier is gain. You're amplifying something. I'm going to multiply it by the gain. Now, what gain value do I use? That's something that can be calculated based on some of the values that we've been recording throughout the semester. Or you could take a small guess. Just for our explanation here, let's use a KP of 100. So that means now instead of adding 5 to 2948, I will be adding 500. And now I have 500, which is 3448, I believe. If I didn't make any mistakes. I'm doing this on the fly like I do a lot of things. So is that increase in counts enough to get the amount of cooling necessary to bring this error back to 0? Remember, as the error changes, this number is going to be getting smaller as it cools, which means that we'll have less counts out here, which means our fan will start up and it'll be slowing down as we approach the set point. So maybe I'd have to increase this gain. Maybe I would have to decrease this gain. In a system that we're tuning, we can calculate or figure out where the gain can be, because you should be able to run the gain up to a point where the system will start to oscillate, where the system becomes unstable. Unfortunately, in the lab situation that we were in, I've never been able to make that system go unstable, no matter how much gain I applied to it. So the concepts behind this particular lab was to introduce this KP term and the fact that it is a tuning parameter that we can adjust. The rest of this lab document explains what I just went over in this little lecture. I have a discussion created in the Blackboard discussion board for you to answer and analyze the program that we're using. Now, the program that we're using, and let me get down to the program. Uses a mixture of ladder logic, structured text, and function block. There are also 3 subroutines to scale the process. I did one in ladder, I did one in function block, and I did one in structured text. Oops, I didn't mean to erase or scribble that out. One day I'll get used to this pad. And structured text. And I want you to take notice that I'm using a tag over here called HMI scaling method and checking it to be a value. In this case, 2. In this case, 0. In this case, 1. And depending on that value, I'm going to be running one of these subroutines, and only one. Because they all do the same function, they just do it in a different way. And I did that to demonstrate to you that things can be done in different formats, but also to show you or to teach you, is there a better way to do it than not? So one of the things I wanted to also introduce with you is in the function block program, there is a new instruction. And that instruction is called scale. SCL. It is only available in function block. You cannot, if you can't use it in ladder, you can't use it in structured text. And the scale instruction does all the math for us. It does all that scaling math. It does that mx plus b calculations for us. All we have to do, though, is we have to provide it with the process variable, which we already know because we're measuring it. We have to supply it with the max PV counts, the min PV counts. So you still have to know that. We're going to be supplying it with the max process temperature and the min process temperature. So those of you who were working in the lab, if you remember, this would have been the values used for the universal transmitter, and these were the values of our counts. So you still had to know those values. I mean, it's not that smart that it can figure all that stuff out. And once you supply it with these values, it does the calculation and gives you the output in engineering units. So it's a real nice instruction. I use it a lot. There are other ways to scale it though, and you'll just see that I've done the same thing in structured text, and I did the same thing in ladder logic. Now, one thing I also wanted to make you aware of is in this particular rung, I'm calculating the percent fan speed. And I created a user-defined instruction, and I called it an FSP for fan speed. You can take a look at this if you'd like. Unfortunately, we don't have the software available to us online so you could actually see this. But I'm not going to hold you responsible for something like this at this time. It wouldn't be fair to you or to me, actually. But you can see I created this instruction, and I wrote it in structured text. But I made it available as a ladder instruction, as a function block instruction, or you could use it in structured text. So in the Studio 5000 software, we can do user-defined instructions. I actually did that in Lab 1 with the random number. That was a user-defined instruction. CCW has the same functionality, and my plan is to actually show you how to do that in CCW. Okay, I believe that's all I want to say about this lab. Again, there is a discussion topic in Blackboard to discuss this program. There is actually another thing I want to talk about. I had said to you about that scaling subroutine only runs, only one of them runs at any one time. On the HMI screen, there are 3 buttons, and there's a picture of the HMI screen. Actually, let me see if I can find that. Well, maybe I don't have it in this document. There is a picture of this HMI screen. I thought it was in this document. Oh, it's not. I apologize. It is not, because we're not using the HMI for this. I apologize. But anyway, there will be 3 buttons, one for ladder, one for function block, one for structured text for the scaling. And these buttons are something that they're called interlocking buttons. We're going to talk more about that this semester, even online, because if everybody can get CCW up and running, I'm going to have you create some HMI screens, because CCW can be used to do that. You can't simulate the HMI, but you can at least get some experience creating them. And then I'm going to show you how to zip them up and send them to me so I can look at them. But these are interlocking. If you're familiar with the old style car radios, they had push buttons that you can set to your favorite channel, so that if you pressed this one, these 2 would pop back out. If that one was pressed and you pressed this one, this would pop back out. So you could only select one at a time. They're actually called radio buttons. So that's how that would be selected. And then if this one was selected, it would create a value of 0. If this is selected, it would create a value of 1. If this is selected, it would create a value of 2. And those were those values you saw in the equal instructions. So they were coming from the HMI. And I thought of just one more thing. There is a subroutine that I created in structured text. On the HMI, there is a display that is a graphical text display. It's called a multi-state indicator. And in that multi-state indicator, you can tell it what color you would like it and what text you would like to appear in it. So based on some status, from the program, I created this multi-state indicator to have 6 different functions. So if these 3 parameters are true, HMI status will be a 0. And that display will display the value of auto cooling and auto heating, manual cooling push button, and HMI is invisible. So I turned off the visibility of some buttons also. And if these 3 tags values are true, HMI status is 1, which says auto cooling and manual heating on. And then I made some other things go invisible. Now I don't expect you to understand all that yet, but in the discussion, I'm asking you to analyze this code just as code. So just know that this stuff here is sending a value 1 through 5 to this multi-state indicator to display to the operator, to the user, a different color and different text to let the user know what status the system is running in. So that said, I'm going to let you go. Keep up the good work. And again, the discussion topic is posted to analyze this particular program. My plan is to have you reproduce this program along with the HMI using the CCW software. So we got a lot to learn, and I'm trying to make this as beneficial as I can under the situation that we're in. So guys, hey, hang in there. You're doing a good job, and I'll talk to you soon.